Okay, let's look at problem 3 of this exercise sheet where you have been asked to develop a subtractor circuit. Now, in the class, we did adder circuits, and what you're trying to do here is just design subtractor in a very similar way. Now, to understand subtractor circuits, I think let's just do a very short revision of normal subtraction. Okay, so let's say you want to subtract two numbers and you want to do, let's say, 4 take away 3. Now that's fairly easy and your answer is 1, right? That's it. But what if you had to do 3 take away 4? Now, as soon as you do this, now don't go into integers here. Let's just work with natural numbers, right? uh, and you say, or whole numbers, and then you say, well, this subtraction can't be done. You can't take away 4 things from 3 things, right? So what would you have to do? You would have to borrow from this side, right? And if you borrowed, what you get is you get 13, and then you could do 13 take away 4, which is 9. And therefore your answer here consists of the difference here, but also, so uh, let's call the difference D, but also there is a B, a borrow, or let's say B out. Okay, so if you're making a subtractor circuit and you're subtracting two numbers, A and B, or right, so let's say you're subtracting two numbers A and B, one of the outputs is going to be your difference D, but and that difference B probably is equal to A minus B, right? But there is also a case where A can be less than B, and therefore your subtractor will not work. It will be an invalid output if you just do A minus B. And in that case, what you want is you want another output called B out, which tells you whether you have borrowed from the other direction or not. All right. So that's what we are trying to make. So if you want to make a circuit like that, okay, this kind of a circuit, this would be probably something corresponding to the half adder in adders, and this is a half subtractor. Why is it a half subtractor? Because there is no borrow in, right? And we'll come to that in just a moment. So let's just write the truth table for this kind of a circuit. So you have A and B as inputs, you have D and B out as outputs. Okay, so you have 4 combinations of the inputs. And what is your D going to be in each case? So in this case, 0 minus 0, difference is going to be B, and is going to be 0, and there's no borrow. So that's fairly straightforward. Now 1 take away 0. Let's take a look at this case. 1 take away 0. I'm going to leave this case till the end. So 1 take away 0 is 1. Okay. So the difference is 1, and we don't need any borrow. 1 take away 1 is again 0, and no borrow here. Now 0 take away 1, this case is different, right? Because if 0 take away 1, the difference, we don't know what the difference is, but the difference cannot be found out unless you have a borrow. So your B out is going to be 1. So you have a borrow. And once you borrow, what happens to this number? This becomes 1 0. So 1 0 minus 1. 1 0 is equivalent to decimal 2. So 2 take away 1 is 1. So you get a difference of 1. Okay, hopefully this makes sense. And so that's our truth table. And if this is our truth table, we can write the Boolean expression for D. So what is our D going to be? D is going to be A bar B plus A B bar. You can see that A is taking 0 and 1 and B takes 1. So A bar B plus A B bar. Okay, so and that, of course, I'm sure you recognize that this is an XOR gate. Uh, and then you have B out. And what is B out going to be equal to? B out is simply this term, isn't it? A bar B. So that's your B out. So that's your half subtractor. And you can make a logic circuit for this. I'll leave you to do that. Now, if you have a half subtractor and you say, okay, I want to actually subtract. Remember that in problem 3, you've been asked to do a 4-bit subtractor circuit, right? So let's let's just think about, again, take the analogy of a decimal subtraction unit and see how that works. So let's say you're subtracting 2, 8, 7, 6, and from this you are subtracting something like 1, 9, 8, 5. Okay, you're doing the subtraction. Now the first subtraction is fairly straightforward. 6 take away 5 is 1. You didn't need any borrow, so you can say the borrow was 0 in this case, right? But when you want to do 7 take away 8, you have to borrow from here, right? So you have to borrow 1, and then you do 17 take away 8, and your answer becomes 9. Now when this borrow has happened, the number here has changed. All right, so if this borrow has happened, this number has changed, and that has become 7, and 7 take away 9 is not possible, so you have to again borrow something from here. So this becomes 17, and 17 take away 9 is 8, and again you have borrowed something, so this is 1, 1 take away 1 is 0. So you see, now if you look at this 8, you can see that there are borrows can work in two directions, right? It may be that the 8 is giving a borrow to the uh, digit which is before that, or it is taking a borrow, right? And we need to think about both these factors when we are designing our subtractor. In the previous case, we only thought about borrows that are coming in, which is this borrow. We were only looking at this borrow, right? But we also want to be thinking about this kind of a borrow. And so we are going to take into account both these and build a circuit called the full subtractor. And our circuit basically looks something like this. So what we have is, we have two digits coming into our subtractor A and B, which we want to subtract. But along with A and B, we also have a borrow in. Borrow in, we call it borrow in because it is an input to our full subtractor. And at the output, we have difference and we have a B out. Okay, a borrow out. Now let's take a look. I think if you write the truth table, you'll understand what I'm talking about. So we say A, B, and B in. Those are our three inputs. And our outputs are D and B out, right? And we have 8 combinations. So let's just fill those in. Okay, so the first subtraction is 0 take away 0, and there is no borrow. So there has been nothing borrowed from A before. Okay, so that's fairly straightforward. The results are just 0 and 0. Now take a look at the next problem here. In this case, you're doing 0 take away 0. Okay, so let me write it here. So you're doing 0 take away 0, but there is a borrow in, which means that something has been borrowed from this one before, right? So this is not 0, but something has been already borrowed from here. Okay, now if something has been borrowed, uh, the borrow could only have happened if there was a borrow from here first, right? So if you borrow from the left hand side, this becomes 1 0, and then you borrow out here, so this becomes 0 1, and then you subtract 1 and 0, and the result is 1. Does that make sense? Okay, let me kind of repeat this because if you understand this, I think all the rest of the truth table will make sense. So what we are saying is, we want to do 0 take away 0, but imagine that the subtraction, that the problem was something like this. So you had like this, and then you have 1 0. Okay, so you're subtracting this. So when you wanted to do 0 take away 1, you can't do it, so you borrowed something from here, but that's 0, so you can't borrow anything from here, so you'll have to borrow from here as well, right? So if you borrow from this one, what happens to the number here? This becomes, let me write in blue, this becomes 1 0. And then you have this borrow going out. So if this borrow goes out, what happens to this number which was 1 0? It becomes 0 1, right? So this becomes 1, and so from 1 you take away 0, so you get 1. You see, so this borrow we are calling it B out, and this borrow we are calling B in. All right, so what's the result here? So there is a B out which is 1 and a D which is 1 as well. So you have 1 1. And similarly you can do this for the other cases as well, and what you would see is your results turn out to be 1 1 0 1 1 0 0 0 0 0 1 1. Okay, so let's take one more example and just take a look at this. Let's take a look at this and let me explain what's going on here once more. So what do we want to do? We want to do 0 take away 1. Okay, and the borrow in, that is this borrow, is 0. So there has been no borrow here. Okay, so there has been no borrow, so this is just 0. So if we want to subtract this, but to subtract this we'll have to take a borrow from here, which means that this becomes 1 0, and so it's 1 0 minus 1, that is 2 minus 1, which is just 1, and the borrow is going to be 1. So the difference is 1 and the borrow is 1. Now what happens if B in was 1, if there had been a borrow here? So even in that case you'll have to borrow from here, so B out is going to be 1, but then you borrow from here, you have taken that borrow, so 1 has gone here, so this 1 0, this 2 becomes actually 1, and 1 minus 1 will be 0. So your result is 0 and your B out is 1. Okay, so that's your truth table for the full subtractor, and you can look up the solutions for the simplification and how you can get the uh, Boolean expression and the digital circuit corresponding to the full subtractor. Okay, so now let's say you have a full subtractor, and what you want to do is you want to subtract a 4-bit number A3, A2, A1, A0 and B3, B2, B1, B0. So how would you do this subtraction? Well, the way to do the subtraction would be, first of all, you'd have to subtract. So when you're subtracting, you want to subtract A0 and B0, right? So you want to say, okay, here's my subtractor. The inputs to this subtractor are A0 and B0, but this is not going to have any borrow because there is no numbers on this side, so there's going to be no borrow in, and the difference here is just going to be D0, right? And it will have a borrow out, so let's call it B out 0 or something like that. Okay, so this is a half subtractor, and then we will have another full subtract. Here you have a subtractor which is taking A1 and B1, giving a difference D1, but A1 and B1 are subtracted depending on what this borrow is, isn't it? If this number required a borrow, that subtraction is going to be different. So it's got 3 inputs, so this is a full subtractor, and it's got another output which is B out 1. And similarly you'll have another full subtractor here to subtract A2 and B2 and give a output D2, and another full subtractor to subtract A3 and B3. A3, B3, and it gives a difference D3, and this is B out 2, and this is B out 3, right? So that is your subtractor circuit, a 4-bit subtractor circuit. So what we did was so let's just repeat the process. So what we did was we made a half subtractor, then we made a full subtractor, and then we used this half subtractor and full subtractor make a 4-bit subtractor circuit.